In this video, we are going to discuss a problem from physics net exam of 2020, which is about relativistic mass-energy relation. Code number for this problem is 173. The problem says you have a heavy particle of rest mass capital M, and while it's moving along positive z direction, it decays into two identical light particles with rest mass small m each. Right? Of course, the total mass is greater than 2m, which is understandable because the loss of mass will actually become kinetic energy of those two small m masses. The maximum value of the momentum that any one of the lighter particle can have in a direction perpendicular to z direction is we have to choose one of the four options. And let us see how we decide or how we arrive at one of these four options. So diagram for the process is this, that the mass capital M is moving along z direction. At one fine point, it decays into two small masses. Now you see initial momentum is in z direction. So the total final momentum has to be in z direction, and therefore each mass has to have the same value for momentum in a direction perpendicular to z, but in equal and opposite to each other. And so that's the diagram. And since they are equal and opposite to each other, that would cancel out, and the component along z direction will add up to give you the initial momentum. So that is how we choose in laboratory frame. Right? The z direction momentum has to be conserved. So whatever is the initial z direction momentum of mass capital M will become, in this case, suppose if you take speed of each of the mass as u, then it will be mu cos theta plus mu cos theta. Whereas mu sine theta in each case will cancel out. So momentum of each m are the same after the decay and will have same transverse components irrespective of the inertial frame chosen. The transverse component of momentum, initial momentum, are in this case irrelevant actually, because you want to find the transverse component. So what we do is we will go into the rest frame of capital M. If we go into the rest frame of capital M, the whole process looks like this. So each of the mass is going in a direction perpendicular to z, and in the opposite direction. They will each carry the same momentum, let's say same speed v, okay, and therefore the relativistic energy after decay will be 2 times energy of each of the particle, which is root p square c square plus m square c4. But before the decay, there was capital M as the mass, so it's equivalent to the rest energy mc square. Our relation becomes 2 times root p square c square plus m square c4 as capital M c square, which will give you momentum of each of the particle as half of c root of m square minus 4m square. And so from the options given, our choice is option 1. For more of this kind of discussions or videos, kindly visit our website